lecture 12 will focus on two beam interference and especially the arrangement for Young's double-slit experiment, which is an example for wavefront division interferometer. Now, just a recap, the past 4 lectures, actually I would say they are more revision of waves and vibrations. So in lecture 8, we learned about traveling wave, the differential wave equation, what are plane waves, electromagnetic waves, and how they carry the energy, and then we talk about Doppler effect. And in lecture 9, we actually look at harmonic waves of same frequency. When we superpose them, we get constructive and destructive interference, and then we talk about standing waves. And then in lecture 10, we now deal with harmonic waves of different frequency, and that give rise to Beats phenomena. And in lecture 11, we explained about coherence, because that is important for observing interference fringes. So for this lecture, we then move on to just two beam interference. Now, this slide is a little bit, it's similar to slide number 9, and when we're talking about superposition of harmonic waves of the same frequency. So let's just recap quickly. Now we have two waves coming in along this direction and this direction. Basically, this is drawn exaggerated. This angle here is quite small. If you remember previously, we said that the cross beam, the angle must be very small in order for us to observe the fringes. Now, and these two beams are actually plane waves, meaning that the oscillation of the electric field is only in one single plane. So in other words, they are linearly polarized field. So this polarized field, and here they have the same frequency, so they are actually monochromatic. They are of the same color in a sense. So at point P is the point where they interfere, where they meet. Okay, so we can write the electric field for each of this wave at point P, whereby the first one is equal to E01, the amplitude, taking the real part, so that will be described by cosine of Ks1, that's the distance traveled here, minus omega t, that's the frequency, plus the initial phase, which is described here. And for wave 2, it is E02, the amplitude, cosine K, same frequency, same wave constant here, or propagation constant. And S2 minus omega t plus, it has an initial phase here. So where K here is actually equal to 2 pi or lambda. And by principle of superposition, the resultant electric field at point P would then just be equal to the linear sum of the individual wave, which is E1 and E2. Now, E1 and E2, the electric field, if we talk about visible range, and that is about 400 to about 750, that gives you a variation of the electric field at a frequency of about 10 to the power 14 to 10 to the power 15 hertz. That's very fast. And if you were to average them over time, it gives you 0. Over very short intervals, it will give you 0 because there's a cosine function. Now, measurement then of these waves then actually depends on the detected energy of the light beam. So basically what we measure is the irradiance, or the radiant power density, which would be the time average of the square of the wave amplitude. And it is written here as epsilon 0 C. Taking the time average, we have this bracket of this form here of the product, the squaring of the wave amplitude. Now we are using symbol I here rather than initially adding in the second lecture. We were using EE, but so that we don't confuse with the electric field, we'll use I here, irradiance, okay? From now on, we will use the symbol I. Okay, so in that case then, taking the time average, okay, so we write it this way. So it's a dot product, and each one of this, it is the superposition of basically a linear sum, like of E1 and E2. So multiply them out, you have E1 dot E1, E2 dot E2 plus 2 E1 dot E2. We did this written in a similar way in the lecture on coherence actually. So remember there was a rate a term, and so this is the interference term, whereas this would give you the irradiances of the individual wave. So in other words, we can then write it as I1 plus I2 plus I12. Now I12 will represent the interference term. Now if E1 and E2 are orthogonal, then the dot product will be 0. So no interference occur. That means a cross beam at 90 degrees. When E1 and E2 are parallel, then the interference term here would have maximum contribution. Okay. We also have cross view, remember, but the angle must be very small in order to get the interference fringes. Now, then the next question we ask is, can unpolarized light, because just now we were talking about plain polarized light, can unpolarized light produce interference? Well, it is possible, because beam 1 then can be of the unpolarized light. We'll learn more about this in polarization of light. Can be resolved into the orthogonal X and Y component, and beam 2 also can be resolved into its orthogonal component E2X and E2Y. So the pairing the parallel components, it can produce the interference term. So let's look at the interference term, that is I12, which is actually made up of the dot product of electric field of wave 1 and electric field of wave 2. And you take the time average. We have a 2 epsilon 0 C. So just take the dot product. Let's look at it and we expand it. Now, E01, so E1 is given as E01 cosine K S1 minus omega t plus the initial phase, and E2 is given by E02, the amplitude, multiplied by cos Ks2 minus omega t plus phi 2, which is the initial phase of wave 2. So now we are going to lump up the phase Ks1 and phi 1 and represent it by alpha, Ks2 plus phi 2 represented by beta, so that it's easier to write. We want to simplify the dot product now. Now we're going to add a 2 factor here. You will see why we add the factor 2 here. 2E1 dot with E2 will give you 2 E01 dot E02 cosine of, then alpha minus omega t cosine of beta minus omega t. So now we use the trigonometric identity whereby 2 cos A cos B is equal to cos of A plus B plus cos of B minus A. So in other words, now our A is represented by alpha minus omega t, B represented by beta minus omega t, and that will give us this one add on to this. We have alpha plus beta minus 2 omega t. This one minus this minus this, you get beta minus alpha. This minus this cancels off. So then in that case, just now we had equation 8 written in this form now, will then become, remember we put a factor 2 there just now, so now it is useful. So the 2 E01, E02 then will become, substitute 2 cosine of this function with this one, so we have already taking care of that. So it becomes E01 dot E02 cosine of alpha plus beta minus 2 omega t plus cos A. I think we have a mistake here. This should multiply by the whole expression here. So there should be a bracket here. So now we are supposed to take the time average of this dot product. So taking the time average, so we are going to, this is not going to change the amplitude, but we would be taking the time average, yeah, we put the bracket here now, time average of this cost function and also the time average of this cost function. But note here, this time average has got the frequency term and this frequency is oscillating. So when you take it over a certain time, then you find that they all add up to 0. Okay, so because cosine of this varying function will take values between -1 to +1, so this term then cancels off. But let's look at the second term instead now. So the second term, we are going to insert the defined expression earlier on. So we're going to insert this one and this one back into beta and alpha, and that will give us k as 2 plus phi 2 minus k as 1 minus phi 1, and we lump together k as 2 minus s1, that is to do with the path difference later on, plus phi 2 minus phi 1, that has to do with the phase difference. So therefore now our time average of the interference term here, we drop the C and epsilon here, we'll put it back later. So then becomes E01 dot E02 time average of this function here. So we're going to represent K S2 minus S1 plus phi 2 minus phi 1 with delta. Okay, so delta is represented by this, whereby this whole term then becomes the phase difference between wave 1 and wave 2. This will do with the path difference because of the distance that the wave travel to the meeting point, and this has to do with the difference in the initial phases of the two waves. So the interference term then becomes I12 equals to, now we put back the epsilon 0 and C. Epsilon 0 because it is in air, so the time average of this, and that will then be equal to, remember we had 2 of this equals to this, so then the 2 factor drop, so we have E0 C E01 dot E02 cosine of that path difference. Yeah. Now for purely monochromatic field, which is a very ideal, in reality we're not going to get that, then delta would be independent of time. So in other words, we can then just write the time average. We drop the time average and that's equal to cos delta. But in reality, in real fields, they are not perfectly monochromatic, so we have to be careful because we need to treat that time average term. Let's look at the individual irradiance terms, I1 and I2. So how do we write them? So we start with taking the time average of E1. So the dot product, taking the time average, will, and E1 is actually equal to E01 cosine alpha minus omega t. So squaring that will give us the amplitude squared, which we take out of the bracket, and then this is the one that has a time component. Now squared cosine function, when you take the time average, it will give you half. So in the end, I1 will work out to be half epsilon 0 because the wave is traveling in air, so we're using permittivity of free space, and multiply by the speed of light and E01 squared. And likewise for I2, it will be equal to half epsilon 0 CE02 squared. Now, when E1 is parallel to E2, and then in that case, the dot product of E01 and E02 will just be equals to multiplying E01 and E02. So we already, then we have the interference term, I12, the irradiance, equals to epsilon 0 C E01, E02, time average cosine delta here. And E01, E02, epsilon 0, C here. We can then replace this by 2 root of I1, I2. How do we do that? Well, let's just input this expression into this here. So in the end, we have a half squaring here and root, so half is out. And then epsilon 0 multiplied by this, in the end, is squared, bring out, C squared root and bring out as C. So E01, E02, then in the end, you get E01, E02. So this expression will be equal to half of this. That's why we have a 2 factor here. So in other words, now equation 6, which is the resultant irradiance when we have two interfering two waves, two light waves brought together, then will result in the irradiance from the first source, irradiance from the second wave, and plus the interference term returned this way, where we have assumed that E1 and E2, the two waves are traveling in a parallel direction. Now, in practice, you'll find that E1 and E2 actually they come from different sources. So we already said that there are no source is actually perfectly monochromatic. So in that case, the time average of equation 17 here would be equal to 0. To account for this slight departure from monochromaticity, we will allow phi 1 and phi 2, which is the initial phase of wave 1 and wave 2, to be random functions of time. That means they vary on a time scale which is much larger than the optical period. That's what we're going to assume, but still shorter than the typical detector averaging time. Okay, so in that case, the interference term would then be written. We put the delta function insert into here, but we lump up the initial phase difference here. The time average term will be 0 because the sources are mutually incoherent, because we are now talking about interference of mutually incoherent fields. Okay, so therefore this time average of the cosine delta function then becomes 0, as we have stated over in the first sentence here. So for mutually incoherent beams, the irradiance, the resulting irradiance would just be the sum of the individual irradiances. Okay. Then if we were to look at interference of mutually coherent beams, now the beams are coherent. So let's say we take the light source from the same laser, we split it up and recombine them at a detector. Well, the time average term here may not be 0. Okay, now why is that so? Because each beam, though, they depart from monochromaticity, but they can be correlated because both the beams are from the same source. So if these beams were to travel the path of equal duration before they recombine, the phase difference would actually be 0. So we take phase difference equals to 0, or in other words, this will be equal to this. So this time term, the term that has the time, would then be equal to 0. So what does that leave us? That will leave us with the cosine k s1 minus s2. So if you look at this one has no time term. So taking the time average, it doesn't affect. So we can then write this as 2 root of I1, I2 cosine of k s2 minus s1. All right. So if the beam were to travel paths that differ in duration by the time called delta t, then the path difference resulting from the departure of monochromaticity can still be approximated to zero, provided that this difference in the time, this delay in time, perhaps we can say, is less than the coherence time of the source. Then it's fine. So this coherence time is the time interval in which monochromaticity is working, is present. We already learned that the coherence time of a source is inversely proportional to the range of frequencies of the component that makes up the electric field, which was given in this expression. So within the coherence time of tau 0, therefore the electric field would travel an associated coherence length given by, just multiply the time by the speed of light. So that gives you the coherence length. Okay. So now we have assumed that this difference in the path lengths traveled by the beam, assuming that they come from the same source, okay, is considerably less than the coherence length of the source. In other words, the path difference here is less than the coherence length. So therefore, the electric fields are mutually coherent. And if they're mutually coherent, we can then define the interference term. So the irradiance of the combined field would still be as we have came up with derived before this. Okay, so we have the interference term, where delta now is the total phase difference at the point where they recombine. So delta is accumulated resulting from the path lengths traveled by the respective beams. And we also have to take into consideration the shift in phase when any of these paths incur a reflection. Okay, and also we have to take into consideration if any of the path were to go through a different medium. Okay. So in the region where the two beams overlap, then the relative distances traveled by the beam 1 and beam 2 is different at different observation points. So the phase difference delta is also different. So if you change P to P1 or P2, then you also would get a different phase. So because of this change in phase difference at different position, then cosine delta then will take an alternating maximum and minimum value. And that is the one that gives rise to the interference fringes. In other words, you have a bright region, dark, bright region. So we were talking about creating the interference fringes, right? So whether the interference term will give a constructive or destructive interference, it all depends on the cosine delta function. Now, cosine delta will be larger than 0. When it's larger than 0, that will give us constructive interference, as you can see here. Then the irradiance would then be higher than I1 plus I2, but lower than I maximum, where the maximum irradiance is actually given by I1 plus I2 plus 2 root of, well, maximum irradiance is when cosine delta equals to 1, so that will be 2 root 1 I1 multiplied by I2. This occurs when delta is equals to even multiples of pi, because the disturbances would then be in phase, right? So now, and cos delta will be below 0, will be negative when we get destructive interference. And then the resultant irradiance would then be higher than the minimum irradiance, but lower than the addition of the individual irradiance. And the minimum irradiance is actually defined by the point where cos delta, the condition when cos delta is equals to -1, and that occurs at every odd multiple of pi. is even, this is odd multiple of pi, okay? So in that case, we have I1 plus I2 minus 2 root I1, I2. So in the case where the two beams, the irradiance is not equal, that is I1 is not equal to I2, we will have the resultant irradiance varying in according to cosine function, whereby it will be oscillating maximum given by I max, minimum given by I minimum. That is when we have a total destructive, when we have total destructive interference, and when we have when cosine delta is equals to 1. So we have constructive interference here. So this level here, then you see the base here, the most minimum has got a certain level of intensity. Now this would be the background irradiance level. But if you want good contrast, you would like to make this background drop to 0. Then you will have better fringe contrast. And how do we define fringe contrast, or what we would call as visibility? And that will be equal to the maximum irradiance minus the minimum irradiance divided by I max plus I minimum. So substituting all this expression into it, you will find that in the end, now you can work this out slowly later, you will find that it will be equals to 4 root of I1, I2, 2I1 divided by 2I1 plus 2I2. Now if I1 is equals to I2, let's say it's equals to I0, then this will be 4I0. This will be 2I0 plus 2I0, and that will be 4I0. And 4I0 divided by 4I0, that will be equals to 1. So you get the best visibility when it is equals to 1. If they're not the same, then you will get a value that's less than 1. So contrast will not be the best. Okay? Now, here is when we have the best contrast, and the maximum will have a value of 4I0. That is 4 times the irradiance of the single source. And that's how we come to it. So if it's equals to, both of them are the same, so substitute into the equation for the resultant irradiance, and this will be 1 plus cos delta. Now 1 plus cos delta is equals to 2 cosine squared delta over 2. So that will give us 4I0 cos squared delta over 2. Okay? So like I said just now, we will have the best contrast when visibility is equals to 1. We will now apply what we learned about interference into Young's double-slit experiment. And here, if we have a monochromatic light source, light beam that's coming towards here, so we let it fall on a single slit, and from this single slit, it will then create this spherical wavefront. So this is like a point source in the sense. Then it creates this wavefront, and when this wavefront arrives at these two slits here, this is the plane of the double slit. So this from the single wavefront will be sampled. So we have what we call wavefront division, because you're taking part of that wavefront that arrive here at the same time, the same wavefront that arrives here as well. So you select, or rather you sample part of this and you sample part of this. So, and then you allow this part of this wavefront to pass through slit 1 and slit 2. So then they will then grow, and here also will grow until they reach this screen, until it falls on this screen. So let's pick a point P on this observing screen. And we're going to assume here that the distance between the slit, that is what we call the slit separation, will be very small when we compare to the distance where we put the screen to observe the interference fringes. Though in this diagram is drawn to be rather large actually, but that's because so that we can see all these angle more clearly. Then we have a line from the center that separates the two slits up to the point of observation. Now, you will find that OP, okay, and then we have another line from S1 to P, and another line from S2 to P. So this would be the path described by S1. This would have a path length described by S2. And we are, because this is so small compared to this, so OP is almost perpendicular to S1Q. The S1 here will be equals to QP actually. So, but because, like I said, this angle, a small angle approximation, we can take this to be almost perpendicular to here. So then, the path difference between this path and this path will be S2 minus S1, that is equal to delta. So delta, if delta here is equals to integer numbers of wavelength lambda, then the wave that arrives at P, they would be in phase, so you have constructive interference. But if it is equal to half multiples of half lambda, okay, half lambda, then you find that it would arrive out of phase by 180 degrees. So they will have destructive interference. Okay, this would be half, then 3/2, and then we have 5/2. So, and the next one will be like 7/2 lambda. Yeah. So in other words, then you will see that as point P moves along this to different position along the screen, so you'll find constructive interference, destructive interference, constructive interference if they meet these conditions. Now, we would now like to write this path difference in terms of A and theta. So looking at just this triangle, which we have taken it to be almost almost perpendicular, so it's a right angle triangle. Then you'll find that delta would actually be sine A sine theta. Okay. Now the condition for constructive interference at point P for Young's double slit experiment then is equals to S2 minus S1, which we denote as delta when it's equals to integers multiple of lambda, and that when that is also equal to A, that is the slit separation multiplied by sine theta. And the condition for destructive interference basically is when this term is equal to n plus half lambda. Now the path difference can be related to the phase difference. Well, when the path difference is divided by lambda, that will be equals to the phase, right? And 1 lambda is equivalent to 2 pi. So then in that case, the path difference that is equivalent to the phase difference delta that is correlated to the path difference delta, they are related through a 2 pi over lambda factor. So just now, earlier on, we actually derived, we're assuming that because we are splitting equally the two slits, we're splitting equally the part of the, we are sampling part of the wavefront, so the intensity of these sources, let's call it, from S1 and S2 would have the same irradiance, so we can then use this expression. So that will be equals to 4I0 cosine squared delta O2, which we derived in about 2-3 slides ahead. before previously. So this is equals to, then delta, you substitute 2 pi delta over 2 lambda, 2 cancels, you get pi delta, and delta here you get substitute a sine theta over lambda. Now, then we are saying that let's sine theta. We will assume that this one is very small, this one is very large. So taking small angle approximation, sine theta can be approximately equal to tangent theta. Then that will be equals to y divided by L. So then we substitute sine theta with y over L. So that gives us cosine squared pi a y over lambda
L.
We have the intensity equals to 4I0 cosine squared pi a y over lambda L. Now, for constructive interference to occur, that's where the bright fringe is going to occur. So at points when that's going to occur is when this cosine function equals to plus or minus 1, because when you square it, it becomes 1, and you will have maximum intensity, which is or irradiance, which is I equals to 4I0. And for destructive interference, that's for dark fringe, that's when this term is equal to 0 and I will be equal to 0. So let's do the bright fringe. Okay, for bright fringe, when this cosine of this term goes to 1, that's when pi a y, let's represent that representative of that position, which is an mth position or mth fringe, then divided by the lambda at L, when that's equals to integer multiples of pi. So pi cancels, then you will have ym is equals to m lambda L over A, where m can be taken from 0, plus minus 1, plus minus 2. That is if your center reference is y equals to 0, so it can be above or it can be below y equals to 0. And you'll find that the separation for between successive bright fringe will be, you can just take y plus 1 and at the position of ym. So the difference then, delta y, would just be equals to lambda L over A. Now, if you look at this expression here, if you want this fringe to be wider apart, well, we can do that if we put the screen further away, or we can use a wavelength which is towards the longer wavelength range. So instead of maybe blue light, we like to use red light, or we can make the slit separation smaller. Okay. Now here's an example where laser light passes through two identical parallel slits. Well, if you use a laser light, then you don't need that single slit put before the double slit. But if you use a monochromatic light source, maybe a sodium light source, then you will need that single slit put it to be in front. That's before the the double slit. Yeah. So using just a laser light beam, so let it pass through the parallel slits, which are 0.2 mm apart. So, and the screen is at 1 meter away from the slits. So, and you want the interference maxima to be separated by 3.29 mm. So what kind of wavelength are you going to use? Basically, that's very simple. We just use the equation given by delta y equals to lambda L over A. So lambda then would be equals to delta y over L multiplied by A. So you just substitute this value in terms in meters, and this also convert to meters divided by 1, and that gives you 658 nanometer. And if you were to use that irradiance equation here, so then it will work out that your irradiance will vary according to 4I0 cosine squared of 955 per meter multiplied by y. Now, besides the Young's double slit, we can make virtual, well, the two double slit seem, it becomes like two sources which are coherent, right? But instead of using double slit, we do a certain arrangement that will give us what we call virtual sources. For example, the first one that we have would be using a mirror. So we have a source at a certain off position here as S here, and we will have this light source giving out beam. So we have the beam that is not reflected, that is falling directly on the observation screen. Now the screen is perpendicular to the mirror surface. So the other beam would be the virtual, come from a virtual source, which happens to be the image of this source by the mirror. So the reflected part of the beam will be the pink part, and the part where they overlap is where we get the interference fringes. So the virtual source now is S prime. And the position of bright fringes will then be given taking the reference here as y equals to 0 when it's equals to m lambda L over A. Now next, we will have Fresnel's double mirrors. So in this case, we have the same source to be placed above the mirror. But in this case, instead of single mirror, we are getting a double mirror, which are one of them is slightly off, lifted off the axis here and at an angle theta. So if you look at this, this portion of the beam will be reflected by the first mirror. That is the red part, or rather the pink part. And then the other part will be reflected by this second mirror. That will be the green part. And the part where they overlap, that's where it's going to give you the interference fringes. And we define this line here. This line here, yeah. So in other words, basically for this mirror, then this would be our virtual source. For this mirror, which you draw a line inclined this way, so for that mirror, so equal distance down will be S2. S2 here will be the other source, but it's virtual. So the light seems to come from this and this source. So the line that separates this source passing through the point where the mirror meets, right through that, that should be the center axis, center of the axis, and that's where you define your distance, yeah. And for the mth fringe, it will be given by m lambda s divided by 2 d theta, taking theta to be small, so that it will be in radians. And d would be the distance of the source to the point where the mirror meets. Big D would be from the point where the mirror meets to your screen. That would be very long, far away, distance away. So S will be the sum of D plus big D here. Okay. And another way of producing or creating virtual source is by using by considering refraction, beam passing through prism. Here in this case, it's called Fresnel biprism. Well, we can think of here you'll find that it is equal angle here. So we have source at the center, and this beam comes here, refracted, and passes through this part. Okay. And let's take this portion of the beam and passes through, because in this case we would have some refraction as well, and then it passes through this part. So projecting this backward, it seems as if it's coming from source 1. And likewise on the other part of the prism, biprism here, it will be as if it's coming from source 2, virtual. It's actually, we consider that a virtual source. So the distance from here to here would be A. So this is A over 2. And this will be a very small angle of inclination. So at the portion where the two beams overlap, that's where you will see the interference pattern. Okay? All right. The learning outcome for lecture 12, you should be able to describe the two-beam interference, and you should be able to derive the interference term. And you should be able to explain the outcome of interference of mutually incoherent and coherent fields, and you should be able to describe and explain Young's double-slit experiment, including deriving the expression that would relate the mth fringe, okay, to the slit width, not slit width, but slit separation rather. Now, and then you should be able to describe other wavelength division optical system, those that uses the virtual sources, those examples that I gave you. So in this case, basically we are focused more on wavefront division interferometers. Thank you. What we saw was all this interference pattern, but we are observing those patterns, which are all these red lines here. Okay, so we get the interference pattern. But the intensity level of each of these bright fringe is actually varying. It is actually being kept by another broader envelope here. But that broader envelope, which is the blue dotted line, is actually due to diffraction. Well, let's cover one of the slit. What's going to happen? Then you will not be able to see these red fringes. Instead, you will see a pattern with a bright central maximum and very low intensity at the edge, which actually is the blue envelope pattern here. So this is due to diffraction. Okay, so it is actually Fraunhofer diffraction of a single slit. We will discuss this in probably about 3 lectures later.